I don't think it's using my headset at all.
Okay. So I suppose we are live now. Okay. So hello everyone, welcome to another session of MRI Together. So this session is on open initiatives from all corners of MRI. So we'll have 4 speakers for this session. So the first two speakers will speak in the first hour, and then followed by 10 minutes discussion, and then followed by another 2 speakers in the second hour, and then another 10 minutes discussion. So if you have questions, please post on the right side Q&A session or in the chat, that's okay as well. So we'll have our first speaker, so Eneko from BCBL Spin, and he will talk about TEDANA, analysis of echo time dependent fMRI data. So Eneko, stage is yours if you want to share your screen.
Thank you, Marcel. Just to check that you can see my slides. Can you see my slides?
Yes, we can see your slides.
Awesome. Well, thank you, Marcel, and everyone involved in MRI Together. First of all, I'm sorry if I yawn or sounds very sleepy. It's 7 a.m. here. So yeah, I was invited to give 2 talks actually about TEDANA, and I'll be mostly covering a very brief introduction to multi-echo fMRI, especially for those who are new to the technique, and also telling you about why or how multi-echo fMRI can be good for noise removal. And then I'll move on to what TEDANA, the software, actually is, but also talk about the community aspect of TEDANA and the challenges we have faced involving developing this tool and how you can contribute to TEDANA. I hope it's interesting for you, because when I was invited to give a talk, I wasn't sure what I was going to talk about. So with functional MRI, we are quite used to acquiring an image per TR, right? And we usually optimize or try to find an optimal echo time specific for a brain region that we're interested in, depending on our research question, or we can try to get a kind of like optimal echo time for all the brain. So in these cases, we obtain a time series per voxel. We could call this way of acquiring data single echo fMRI. Now, what is multi-echo fMRI then? Well, it is very similar in its concept, and as the name says, multi-echo fMRI consists of acquiring more than 2 images of different echo times within the same TR. And in this case, we obtain as many time series as per voxel as echo times or images that we acquire within the same TR. Which means that if we acquire 3 images of different echo times within the same TR, we obtain 3 time series of fMRI signal per voxel. And we can adjust the values of echo time to find or to optimize for the best contrast of different areas of the brain. And you may wonder, why do we do this? So one of the reasons to use multi-echo fMRI is that we can recover signal that is usually lost in single echo acquisitions. So for instance, on this image, the first echo on the top row has less dropout, and later echoes have better gray and white matter contrast. So the idea is that we can use all this information to improve our signal to noise ratio. And then if we go into the actual mathematics of multi-echo fMRI, and we assume that the signal follows a mono-exponential decay model. I'm not going to get very much in depth into the maths, but the idea is that we can separate two components of the signal. So I don't know if you can see my pointer, but we can separate the S0 component from the R2 star component. So the S0 here would be related to the net magnetization of the signal, and the R2 star changes would be changes in volt signal or in indirect neuronal activity, which is what we're actually interested in usually. But not only that, if we actually normalize our signal to % signal change with respect to the mean, we can see changes in R2 star are linearly dependent in the echo time and at the bottom of the slide, while the changes in the net magnetization are independent from the echo time. So this gives us some, basis to work on separating different components of the signal, which might be of interest. And here actually you can see how the different terms behave in completely different ways. So for instance, the changes in net magnetization or S0, you can see would be shown with the red line, while changes in T to star, or which is the inverse of changes in R to star, these are shown in blue lines, and you can see that their behavior based on the echo time and the time is very different. So this allows us to separate the two components. And so how can we denoise our multi-echo fMRI data then? We have seen that there are two different components of the signal that we can use. So how can we actually denoise the data? So there are two main ways to do it, I would say. One is the optimal combination, and in this case, we will not be separating these two components. We would just be using all the information available to find a cleaner image. Or we can, as I said, go into those two components and separate them somehow. Multi-optimal combination of echoes is very simple. So what it does is if you acquire 3, 4, 5 echoes of 3, 4, 5 time series, all you have to do is calculate a weighted average. And this allows to reduce the thermal noise and shows quite reliable improvements if we compare with single echo data. And this can be very easily calculated with software such as AFMI, fMRI Prep, or TEDANA itself. But now let's get into the most interesting part, and TEDANA itself. So among those techniques that actively separate the two components of the signal, I would say that the most famous way of doing it would be multi-echo ICA, and that's where TEDANA comes in. But there are other ways to denoise the data or separate these components, such as multi-echo parametry mapping, which blindly estimates changes in the R to star component of the signal, or well, there are other methods that I link here as well. So now that I have introduced the goal behind TEDANA, so the actual multi-echo ICA part, I would like to briefly explain what TEDANA does in the inside, right? What happens when you run TEDANA? So first, as you can see here on the right-hand side, there's TEDANA calculates the signal decay, mostly to get the T to star map, and then calculate or optimally combine the different echoes. And this optimal combination of echoes is given to the PCA step, which is done for two main reasons. One of them being reducing the dimensionality of the data, and the second one being identifying thermal noise and removing it from the data. So once the dimensionality is reduced, TEDANA runs an IC8 step to find the finite components that are later classified into, this is bold-like, I like this, I want to keep it, or this is not bold and I want to remove it from the data. And so once this classification is made, we can denoise based on this classification. And then after that, TEDANA gives you the option to remove some spatial noise. So as you can see in this example, we can find ICA components that are clearly artifacts that we want to remove from our data, like multiband or head motion or CSF pulsations, and TEDANA allows us to get rid of this. So that's enough about the theory, let's say, about multi-echo and what TEDANA does. Now I want to tell you more about who's involved here and the community around TEDANA, which I think might be interesting for this conference. So TEDANA was originally developed as a place for multi-echo fMRI denoising. And it started as it was originally defined in the multi-echo ICA code. The problem with that code was that it was not very understandable. It was not modular. It was not adaptable. So TEDANA tried to, get that code and make it as understandable, modular, adaptable, easy for everyone to use. And the original code was written by Pantekunde, but then Olivier Dupré started TEDANA to bring these improvements in. Dupré has had around 20 contributors from various countries and institutions, and we have expanded to welcome additional multi-echo fMRI processing approaches to support communal resources for multi-echo fMRI, whether or not are directly involved with the TEDANA software. And we also hold monthly developer calls. We occasionally send a newsletter if we have enough news to share, and have a very active issue board and code updates. And just so you know that TEDANA is, because I don't think I mentioned it, it's a Python package. You can very easily install, run from the command line, or you can also run it from a Python session. And if you want to learn more about the software itself and how to use it to denoise your data, I welcome you to join the Juggling with Data session on Thursday at 12 p.m. UTC, because I'll be giving a tutorial on how to use these tools. So, like I said, TEDANA is more than just a software. It's actually a collection of tools, software, and community related around these echo time dependent analysis. So the umbrella of TEDANA covers a number of overlapping but somehow distinct ideas related to multi-echo analysis. And this scope includes collecting multi-echo data, so acquisition, how to combine those echoes together, so there's a combination part, optional noise removal, and also data visualization and answering to questions around the community. But we also have there are other packages or software or documentation that have been created around TEDANA that I would like to show you today too. So for instance, MAPCA is the Python package that runs the PCA stuff used in TEDANA. This is just a Python translation of the dimensionality estimation method in the MATLAB GIF package. We have also come up with Recom, which is a web app that provides quite an easy and fast way to go through the IC components that TEDANA classifies, and then it allows you to change this classification, because TEDANA's automatic classification is never perfect. So this web app lets you look at your data and change this classification. It actually allows users to save the manual classification in a format that is very easy to use and rerun TEDANA with, to perform a better denoising of the manual classification. We're also working on a Jupyter book that explains the theory behind multi-echo fMRI, shares practical resources for those who want to acquire this kind of data and have never done it. And also it has, or will have, because it's still a work in progress, it will have tutorials on how to analyze multi-echo data with different tools. We also have a curated list of every multi-echo fMRI poster that has been shared at OHPM in the past 3 or 4 years. If you have written any, you're probably there. And then we are also working on a couple other packages that are somehow related to what we do, that are linked here. But yeah, we have also faced some challenges when developing TEDANA and the community around it. So for instance, the expertise required to fully work on TEDANA by yourself is immense. You can have a look at the list here. No one in the team has all of this, no one. So we have to try to complement each other somehow. At the same time, a big challenge for us is that most of the people involved are grad students or have just turned into postdocs, which means that we have to make sure that the code on the project itself survives beyond this period of contribution. That's why we think that a very good documentation and testing suite are very important. And finally, this one is a challenge that we've talked about quite a bit within TEDANA, and that's that it's actually very specific to us, I believe, unlike the previous one, which was more general. But the thing is that we think we are too big for informal governance, but at the same time, we're too small for most of the open source governance models that are documented out there. Yeah. Talking about governance, this is how we do it at TEDANA. So first, I would like to thank Kirsty Whitaker for her guidance over the past couple of years. But yeah, at TEDANA, we acknowledge the leadership of contributors and try to minimize all the administrative burden. We want to, want the work and the code itself to be the ones talking. Then we also try to grow our community and try to find consensus among all or most of our active contributors. But mostly we are a very open group of multi-echo enthusiasts. So we're very open in terms of code and decision making, but we also welcome anyone who is interested in joining our meetings and telling us about their work, giving us feedback, asking for new features, or even just joining our meetings to learn. We have come up, in terms of governance, we have come up with a steering committee that makes sure that the project is on course to meet our goals. And we have also assigned focus roles for the different code-related tasks, so that we make sure that there's an expert that takes care of the different branches and that fit TEDANA. And finally, we have a code of conduct that we have never had to use. So if you would like to contribute, like I said, we are very open to new contributions and are actually actively looking for them. So please join. But for real now, if you have ideas for data processing or visualization documentation, educational content, or have identified gaps, for instance, in what we do, please DM me or join our calls. You can click the link down here. It will take you to our Google Calendar. And also, if you have multi-echo data and would be willing to help us validate and test our methods, that would be very much appreciated too. So like I said, we are very open. So discussions are also very open. And how can you do that? Well, you can start a new discussion on GitHub. This is a new feature that GitHub released not too long ago. So feel free to start a discussion here. Or you can use NeuroStars with the TEDANA or multi-echo tags. I think this is a way most of our users choose to get in touch with us with. And I would say that the TEDANA team are pretty quick and helpful with their replies. So please make use of these platforms to reach us. And I wanted to quickly mention that I'll be giving a tutorial on how to use TEDANA to diagnose multi-echo data on Thursday at 12 p.m. UTC as part of the Juggling with Data session. So please join the session if you want to learn how to use TEDANA and RICA. And with that, I would like to thank the organizers for the invitation. I would like to thank you for your attention. I want to say that these slides are available through my website and using this QR code. So yeah, please do not hesitate to get in touch with me or any one of the TEDANA developers. Thank you.
That's great. Thanks, Eneko, for excellent talk. So let's see if anyone has questions. I see there's a Q&A here. So Sophie asked a question.
Yeah. So the question is, how can early career researchers best be rewarded for contributing to projects like this? I think TEDANA's example is quite a good one. I had it. Yeah. So first of all, we have a picture and an emoji on our GitHub that shows if you have contributed, it will show your face or your GitHub profile picture, and the emoji will tell what kind of contribution you've made. But also, everyone who has contributed to TEDANA will be part of the OHPM posters, will be part of any paper that we come up with, which was the case like 2 years ago, I think, 3 years ago. Oh, last year, actually. Anyway, what I mean is that all contributions are acknowledged via posters, papers that come up with TEDANA, and mostly GitHub. That's the most up-to-date version usually.
Sounds good. So I have a scientific question. So I'm now in the field. But how popular, or is it kind of a standard now to use multi-echo fMRI instead of single echo fMRI? Can you give some comment? If you do multi-echo, like how many echoes you choose? For echo, I know people choose the R2 star value to be the TE, but for multi-echo, how do you choose that? How popular it is now for the fMRI to use?
So I think it's slowly becoming more popular. The biggest bottleneck might be that people do not have access maybe to the sequences. And they have, like, people tend to have many doubts on how to actually have a proper pre-processing pipeline. But we're trying very hard to make all of this information available through our documentation and stuff. So we are seeing more and more people try multi-echo fMRI. In terms of how many echoes, depends on how fast you want to go and all that stuff. Because at the end of the day, you have to put in echo times within TR. So if you want to go real fast, you might not have time for like 5 echoes. But also, if you do not care much about your TR being a little slower, you may want to use more echo times because you will have more information, which is useful for denoising. Because at the end of the day, let's say you have 3 times, 4 times, 5 times the same information. And that at the end of the day helps you denoise your data better. Yeah.
That makes sense. But does that sacrifice your resolution if you fit more echoes in the readout for 1 TR?
Not necessarily. I mean, of course, depends on how fast you want to go.
Okay.
But not necessarily. Nowadays, it should be feasible to go, I don't know, 0.5, maybe a little slower. I'm not an expert on sequencing, so, but I would say, yeah, 0.5, you can easily do 3, 4 echoes.
Okay.
5, maybe, yeah.
Yeah, great. Sounds great. So Sophie has a comment. I think that's great. However, hard to put an emoji on GitHub, your CV, especially academic CV. Yeah.
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 I agree with Sophie. Actually, this is how TEDANA is how I learned to contribute to open source and how to properly use GitHub and all that. So it's a really good learning experience as well.
Yeah. Sounds good. So my last question is, for TEDANA, is it a software that do the fMRI, the whole processing pipeline, or is it just only for denoising?
It is only for denoising, yeah.
Only for denoising.
We recommend that you run TEDANA pretty early in your pre-processing pipeline. But it only takes care of the denoising step.
Okay.
You can use, for instance, fMRI prep, which is now compatible with multi-echo. And it will get to the TEDANA point and run it. And also AFNI has the AFNI proc script that has a bunch of options to run TEDANA as well.
Okay.
But TEDANA is just that small part, well, small, depending on how important it is to you, but
yeah. It's
only taking care of the denoising, yeah.
Take care of the multi-echo and denoising, and then you can pop into other pipelines. Right.
I will actually talk about different ways of doing denoising on Thursday. Because depending on that, you can do different things in your pipeline, yeah.
Sounds good. Yeah, we'll see you on Thursday. I'm looking forward to that hands-on session.
Thank you.
Sounds great. So we'll move on to our second speaker, which is William. So William is from University of Oxford, UK, and he will talk about open tools for MRI spectroscopy.
Right, let me just share my screen. Can you see those slides?
Yes, we can see the slides.
Perfect, and you can hear me all right?
Yes, we can hear you already.
Perfect. Okay, I'll begin. Right, hello everyone. My name is Will Clarke. I'm a spectroscopist working at the Wellcome Centre for Integrative Neuroimaging at the University of Oxford. And yeah, the organisers very kindly asked me to speak about some of the new open science tools available for spectroscopy, or MRS for short. Now, the key principles of MRS are identical to MRI, but the techniques of data acquisition, processing, and interpretation are somewhat different. So let's start with a little one-slide primer on what spectroscopy is. Now, MRI is nearly entirely concerned with measuring the presence, interactions, and properties of one molecule in the brain, and that's water. And in spectroscopic terms, water gives a single signal arising from the 2 identical protons on it, and you can see that here as a sort of single peak in the spectrum. But it should hopefully come as no surprise that there's some other molecules in the brain, and though they occur at a much lower concentration, they are essential to brain function. So the structure of each metabolite or neurochemical, I'm going to be mostly focusing on the brain here, is pretty different. And that means that each has a different and unique spectral response dependent on their structure. And when we acquire signal from the brain, we see a linear combination of all these spectral responses added together, weighted by their relative concentration, and then modulated by things like T2 and the quality of the shim. Now, in MRS, we then try to separate out these individual responses to measure the concentrations or perhaps other properties of each metabolite. And in doing so, we can end up with some nice maps of different concentrations of different metabolites across the brain. So that's MRS in a nutshell, but how do we actually measure the data? Well, I think most people will be relatively familiar with the idea that to measure an MRI image, we have to require some case-based data with a sort of a single point at each location, a single value at each location in case space. We can then Fourier transform that and form our MRI image. So for spectroscopy, we have to do something in addition, and that's acquire an extra time domain dimension of information. We again Fourier transform that temporal response to form our spectral response, and this looks like our spectrum you saw on the previous page. We can then actually combine the two approaches in a sort of 3D or 4D kind of approach, and we can get our images of spectral information and concentration maps. Cool, so due to this special data acquisition and processing, MRS has remained somewhat niche, and so an ecosystem of specialist tools was made, designed for use by experts. And if we kind of think back to the 2010s, typically MRS data was analyzed in one of two quite similar ways. So data in an array of formats was loaded into memory. Many pre-processing steps were then applied by a single program in memory, and then fitting was done, results are generated, those concentrations I spoke of earlier, or one small kind of modification was maybe an intermediate format was written halfway along, and then you load the sort of pre-processed data into a dedicated fitting program, something like LC model. There's some notable exceptions to this, particularly, say, the FIDE and VESPA toolboxes, which are paving the way for what I'll talk about later. And what does this look like in terms of data? And this slide sort of exemplifies what a pre-processing pipeline might sort of look like, and it's really there for analyzing a certain type of spectroscopy, single voxel spectroscopy, that's generating a single spectrum from one volume of interest, and it proceeds in a sort of deterministic analysis pathway. So data is loaded from one of many proprietary formats because the DICOM standard is not well, for spectroscopy, is not well supported by vendors. Then steps like color combination, frequency and phase alignment are applied, all done in memory. And then an intermediate format of our sort of final pre-processed spectrum might be written, but it's often in a sort of ASCII or text format. And then it's loaded into a dedicated fitting program. And again, results, which are these concentrations and sort of uncertainties that you can see here, are then sort of output in a range of sort of formats, so maybe CSV or various other sort of tabular data. Now, in some ways, this is ideal. It's a one-stop shop of high-quality, expert-made tools, and what could be better? You click go, and it all happens. But the first issue here is what happens if you're not an expert and you don't know how to set many of the complex settings you need to control this pipeline for certain types of data? Or what happens if you have a new type of spectroscopy to analyze which doesn't fit neatly into this sort of fairly fixed processing pipeline? And that final point is the crux of the matter. 3 new spectroscopy technologies have sort of appeared on the scene, and they're functional MRS, diffusion-weighted MRS, and high-resolution MRSI. And so these in turn use time resolution to monitor the dynamics of neurometabolites during brain activity. They use diffusion sensitization to measure cell type-specific microscopic structure, or they can dissolve many thousands of spectral voxels across the whole brain. And so for the first 2 dynamic techniques, that's spectral and diffusion-weighted spectroscopy, we now have an additional dimension of information to collect and handle. So we're moving from the sort of static spatial time spectral domain to this dynamic MRS where we have spatial time spectral plus some dynamic dimension, either sort of changing diffusion gradients or temporal resolution. And these dynamic techniques need some new tools. Why? Because they need their own specific customizable pre-processing. They might benefit from some new analysis, say fitting approaches to interpret their signal and mitigate low SNR. And also because they're relatively new, so ideas and new approaches are still being rapidly developed and trialed. So software now needs to be flexible, be modular, be able to be checked and validated as the complexity grows. And then the final, more complex results, as well as intermediate results, need to be shared and kind of validated and compared along the way. So one example of improvements that we could potentially make for that dynamic spectroscopy is in the fitting stage. So this is a recent sort of development in ideas, although not really new if you look at the whole of the scientific field or MRI, and that is that these dynamic techniques' current practice is to repeatedly fit the noisy data independently, and then the noise-affected estimates are subsequently refit to extract that dynamic information, that microstructural or functional information. Rather, what you might want to do is combine the dynamic and spectral fits together in one step. I'm going to talk a little bit more about that later. But finally, these new approaches and also the increased availability of ultra-high field scanners is attracting some new users, which is fantastic, but they are rightly confused as they ask which of the many data formats available for spectroscopy might possibly work with any of their pre-processing toolboxes. And then they might be quite surprised to find out that not all of these data formats are handled by their collaborators processing. And in fact, there's no good way of comparing data or sharing data between the sites and loading them into each other's software. So MRS and spectroscopy has and had a few needs. The first is to be able to easily share data between researchers, both large-scale data set sharing and lower-level sharing for development. The second is to enable quickly extending tool sets in a modular way. That's so new ideas can be tried without having to re-implement every step and then compared and validated. Then we need some greater integration with other modalities. This will help leverage the high signal MRI to mitigate low SNR of MRS and then also help make sense of our results. Finally, we should endeavour to make spectroscopy more accessible for non-expert users. Now, there's been some great progress in this on acquisition with standardized sequences and consensus recommendations, but the analysis remains very difficult. So what's been achieved so far? I'll start with what I think is the glue that holds everything else together, and that's a single standard format that can contain all types of reconstructed MRS and MRSI data, and that's based on the widely used NIfTY format. So this is called NIfTY MRS, and it's a minor tweak to NIfTY, exploiting the header extensions to carry essential spectroscopy metadata. It was developed over the last 2 years by this small group of mostly software analysis sort of developers. And we also published it alongside tools for conversion from those other many formats that we saw on the previous slide. The main things we've achieved is a single target format for all stages of data handling and integration with other MRI contrasts and tools. So we've published this new standard NIfTY MRS, formerly in MRM, and I think that's a great way that these products can give some exposure and to people working on them, and that's been done as this group of analysis tool developers. But we also have made all the tooling examples and the actual standard data storage standard open source and available, and all the ongoing publication of any updates will be made on Zenodo, and that all happens automatically as part of GitHub's sort of continuous integration service. Alongside that, there's a documentation page, and the upshot of this is firstly that we now have sort of adherence to this standard in a range of different MRS toolboxes, and so you can see 3 here with spectral and spatial information conveyed in this standard. And in fact, this is now expanding, I think now in 5 different toolboxes. We've also published a conversion program, SpectroNII, which is definitely inspired by Chris Rawdon's DCM to NIIX. And this tool has the unenviable job of converting data from 16 different formats, all those ones you saw on the previous slides, and numerous subversions to the singular nifty MRS. Again, this tool is open source, and it's been great to see some fantastic contributions from the community, especially for interpreting preclinical data formats from, say, Brooker and variant scanners. But contributions and improvements are still very welcome, and in fact sought for a lot of formats. So by using NIFTY, a format that's widely used in MRI neuroimaging and therefore widely handled by tools which already exist, we immediately reap some benefits. So here you can see how MRSI data, that is multivoxel spectroscopy data, can be displayed alongside fitted results, metabolite maps, and all overlaid on MRI structural images, or just by making minor tweaks to existing tools. In this case, Fossilize, the fCell image viewer. And so by integrating MRS into MRI tools such as Fossilize opens up the possibility of much greater and easier integration of spectroscopy with imaging modalities. And this slide just shows some of the specialized displays available in Fossilize, but it's to showcase the broad range of information available in multimodality studies. By integrating spectroscopy, we hope to make the co-analysis and co-interpretation with other modalities much more possible. So the next tool set I'll talk about is my own, developed with Saad Dubabdi over the pandemic. FSL MRS brings spectroscopy analysis to the FSL stable for the first time. It was created to be a platform to explore new analysis techniques for these new forms of spectroscopy, functional, diffusion, and high-res MRSI. But we also wanted to keep the FSL theme of being relatively easy to use, and it of course allows integration with existing FSL tools, and more on that in a second. So to achieve those aims, FSL MRS is entirely modular, using nifty MRS to glue each module together. The pre-processing is modular and available in 2 distinct environments. The first is on the command line, so individual nifty MRS files can be operated on. Here is how you would, say, do coil combination, and that returns you a processed, dimensionally reduced nifty MRS file. Alternatively, the exact same processing can be applied in an interactive or a scripted Python environment, as shown here, and both processes create the same summary, same sort of outputs, and then summary figures saved either to HTML or appearing in an interactive Python notebook. And this means that we've been able to quickly produce prototype approaches to analyzing new formats, particularly functional MRS. And so let's have a look at that. And here we have a real-life fMRS dataset measured in the primary visual cortex as the subject undergoes blockwise visual stimulation. And if we individually analyze each noisy spectrum in the time course, we unsurprisingly get quite a noisy output of metabolite concentrations, is glutamate and NAA. Now we might expect some signal in the glutamate. So we extend our open source program, fMRS, to implement our idea of simultaneous spectral and dynamic analysis. And in FCell, we do this by defining just programmatically arbitrary functions and temporal dynamic parameters. So for fMRS, this would be a very simple GLM implementation, and then a design matrix which defines our stimulation paradigm. But this could easily be altered, say, to exponential decays and for different diffusion D values. And so we combine the spectral fitting that we've sort of seen with that GLM approach, using an estimated bold-like response of metabolites. And as an output, we can estimate a single subject fit GLM that looks like this, and that's then overlaid on that noisy time course. But okay, what do we do then? And at this point, I return to the idea of open tools and data formats integrating MRS with a wider ecosystem of MRI tools. I've shown how we can visualize data together, but fMRS is the first spectroscopy toolbox to be integrated into a larger neuroimaging toolset. And that brings the benefit of leveraging the vast array of existing tools which exist in fCell. Because, as I said, what should we do after we've fitted a single subject DLM? Well, of course, we should do a group analysis. And for that, we can turn to existing MRI tools, and fMRS implements an interface for spectroscopy into fCell's FLAME tool. You're probably not familiar with FLAME, but it sits at the middle of the higher level group analysis of fCell's fMRI tools. And so using that, we can therefore generate fMRI style Z statistics for each metabolite and P values, or just by formatting this in the right format in NIfTY and with some sort of covariance information conveyed, we get these sort of nice results out showing that glutamate does in fact show significant activation. If we look at a control condition, that's with your eyes closed when you're being shown visual stimulation. So fMRS is fully open source, but that isn't enough to make it easy for new users to use. For that, we also have interfaces for bug reports, documentation, online practicals and video tutorials, but this is definitely still an area that we're working to improve, as this topic remains tricky for those new to the field. Now, this is a point that I should say that I'm not the only one doing these things. There are some great open source packages out there being continuously developed. I'd particularly highlight Osprey, Spant, and Vesper, but also Gannett and Fide get a very honorable mention. So please do go and check out how all of these packages work if you're interested in spectroscopy analysis. And so far, what I think is great is that we've maintained some really healthy competition between these packages. We drive each other forwards in different areas and work together to tackle combined goals. And these packages are amenable for comparison, both sort of already published and sort of ongoing comparison, and that's not per se to rank which is best, but as a constant validation that we're getting things right, especially as we use more complex techniques. The final need on my list was easing access, and for that we need some great, easily accessible education and help. So for that, we've created the MRS Hub and forum, and there you'll find a growing group of spectroscopy users and experts to answer any questions. And I'll highlight particularly Condensed Flashes recently led an effort to amalgamate a huge range of educational resources now available on MRS Hub. I'll finish with two efforts that are ongoing. The first is spectroscopy is being put into the BIDS standard. I won't linger on this because I think we've got two talks coming up on BIDS, so you'll find out more there. But it's now being put into the BIDS specification. And then one of the trickiest parts of spectroscopy analysis, that of performing detailed spin system simulations to create fitting basis spectra, is being led by researchers from Johns Hopkins. And they've got a really nice cloud-based simulation solution, and then a way of sensibly storing, sharing, and manipulating the results. And that's just been submitted to our SMRM. And this will, I think, really help close the loop on all parts of MRS processing. With that, I'm going to conclude and thank the many people who've worked with me on this and in fact continue to work on some excellent endeavors. There's lots more to do, so if you want to get involved, just reach out on MRS Hub. All right, thank you for listening.
That was great. Thanks, William, for the excellent talk. Let's see if we have any questions from the audience. Just checking the chat. Yeah. So based on my understanding, this is a spec to MRI. That's a toolbox that will handle the conversion between of different input types from different vendors to NIfTY, so that it can be streamlined to other pipelines. Is that correct?
Yes, that's correct.
Okay. Yeah.
And so yes, there's this huge range of different formats which are sort of output by different scanners and different models, sort of at different stages of processing, whether they've been averaged and coil combined, and each of them sort of have their own sort of format. So this is a program which effectively is just trying to combine the community's knowledge on how to interpret all these formats, both the data and the metadata that they carry with them, to get to this sort of singular format. One of the major things it doesn't do yet is handle unreconstructed data, so sort of MRSI data, because doing sort of reconstruction in a general sense is very hard, because none of these formats convey any information about the trajectory, any case-based trajectory.
Okay. So what makes you guys make the decision to choose Nifty as the standard format?
So yeah, there was a lot of discussion about this, and various people sort of proposed ideas along the way, because Nifty is not fantastic at storing sort of raw data, maybe for MRSI, but in that case we sort of highlighted the fact that there is already a format out there for that, this ISMRM RD format, which is entirely suitable for holding spectroscopy data as well, unreconstructed. And so we really wanted a format that sort of would be the one that you share sort of your main sort of results from a data sense, which is that sort of pre-processed spectrum. And then also it aligned with a huge amount of sort of data which is already out there. All of these formats are and can be held in Nifty. So that's moving spectroscopy onto a common platform, and yeah, it very quickly brings benefits, being able to use all these different sort of neuroimaging tools, because we're using it.
Yeah, that makes sense. Particularly with the FSL, I guess they use a lot of Nifties, and this integrates quite well with the FSL.
Yeah, no, and I mean one thing is this, the visualization was very, very easy to use and to make a tweak. So all of this extra sort of MRS specific display is a matter of writing a couple of short functions, which then can go into Fossilizer's plugin infrastructure. So you too can modify Fossilize and to make it do what you want. And I think Paul's actually talking about some bits of that later on in the week.
Yeah, awesome. I'm pretty sure writing these softwares and documentations take a lot of time. So can you give some comments on that? Do you think that's worth it, or instead of just focus on developing the algorithms? Any comments on that?
Yeah, you're absolutely right. It does take a lot of time, and then as you release them, maintaining them and responding to community needs and bugs and things like that takes maybe even more time. And yeah, this has been the major part of my sort of research program in the last 2 years. But we're at a point now where we've sort of made the basic tools, using many algorithms which are kind of already out there, or our interpretations of them. But now the whole point of this is that we can go on and do some work in sort of interesting arenas, and in this sort of dynamic spectroscopy, and using the tools that we've made, because this was designed as a sort of to address the fact that these tools didn't exist, and it wasn't possible to extend what was already out there easily at all. So yeah, there's been a bit of work in getting there, but now we're able to do some new and exciting science with these tools. But yeah, there's been a large setup cost, and but it's great to have support from expert software developers at my site, who can really help with getting you directing you to the right way of doing things from the get-go.
Yeah, I'm pretty sure it would be helpful to have some people from the software engineering background, and then really tell us how to do the software development.
Yeah, or just to answer, rip-off code, all those things around, package publication, continuous integration, testing. Those are all the bits where sort of getting their expertise is really, really key.
Yeah, But I'm also glad to see that you guys published some papers on the software platform itself, and at least you guys get credits for your effort in making these softwares, right? So that's great.
Yeah, no, we think that's a really important thing. You know, these tools should be out there and published, and you get credit for them. Yeah. That was the word I was trying to search for in the talk. And I think, you know, now there is some, you know, formal publication routes, right? Like NeuroImage has a toolbox, paper format and stuff like that. So that's great to see.
Yeah. I'm asking this because sometimes when you submit a paper to some journals and they will say, oh, this is the software, and then you assemble things together, and then there's no novelty, and we're not going to accept the paper. So yeah, I'm glad to see other journals, they have, they think about this and then have space for software as well, which is fantastic. All right, great. Thanks again, William, for your excellent talk. So we'll move on to our second hour. So Yan is here. We'll start with Yan Peter. So he will talk about ASL BIDS and OSIPI pipeline inventory. So yeah, I think you're muted, but I think I can unmute you.
Yeah, okay, thank you. I think we both clicked the button at the same time.
No.
I'll start sharing my presentation. So I hope everything works now and that you can see the entire screen.
Yes.
So yeah, thank you again for the introduction. So as you've said, I'll be talking about several things about BIDS and OSIPI. So yeah, I basically want to mention 3 open initiatives that we are using for improving processing of ASL MRI data. So one of them is sharing data using ASL BIDS. The other one is making a pipeline inventory of all processing software for ASL that is out there, which is done within OSIPI. And at the end, I would like to talk about our ExplorASL pipeline, where we try to put all these things together. So to start with, a small introduction on arterial spin labeling. Despite many people probably already know it, it's a non-invasive technique for imaging perfusion. It's mostly used in the brain, where you can label the blood magnetically in the brain-feeding arteries. The labeled blood then travels to the brain, perfuses the tissue there, changes the signal. So when you take a normal image of the brain, this is somehow the signal is influenced by all the inflowing blood. And if you do all this right, properly calibrate, then you're able to extract quantitative perfusion maps completely non-invasively. So this technique has been already known for 30 years. It's a very promising technique already for 30 years. And we are now managing to get the technique to translate it to the clinical research, and also it's sometimes used in the clinics. But of course, things can go much faster. And I would like to talk about some open initiatives that can accelerate this translation. So the first question we have to ask ourselves is it difficult to obtain ASL data? And I actually have to say that now it's becoming fairly easy, because a product sequence is available on scanners from most MR vendors. And if you're not happy with the basic sequence, then there are many advanced extensions of the basic ASL sequence, which are also freely available from several researchers. And there has been a recommendation paper published that lists all the basic ingredients of how you should set up your ASL sequence. So I have to say that it's fairly straightforward to acquire ASL data now, and many people are doing that. But what is now a bit of a problem is what to do with all this ASL data. So plenty of people have a lot of ASL data and don't have that much experience to work with. And there are a few issues with ASL. There's still there's not a one unique sequence. There's plenty of different sequences, plenty of different names, different functionalities. And of course, there's a lot of software tools that can help you process all that. But all these choices, all these sequences, pipelines, that might become a bit overwhelming for new users with not too much experience. And so the question is, if you're new to ASL and you want to find your way in processing all the data, then what to practically do, how to start. And so I would say the main issues with processing ASL data is that there's quite some heterogeneity in the way that data are described and stored. So everybody uses his own way how to store the data, which then doesn't make it very easy to share the data between researchers. Also, there's plenty of tools to analyze the data, but how to choose the one that will work for you, that's also a question. And lastly, if you're new to the field and you just want to use ASL as a tool to aid your research, then you don't want to go into the depths of how to process ASL data. You just want to acquire your data, throw the DICOMs in a tool, and you're expecting to get some results and focus on the science, not on how to process the data. And so in my presentation, I would like to address all these three questions. And first, I'll talk about the brain imaging data structure and its ASL extension that helps to organize and store the data. Then there's the Open Science Initiative for Perfusion Imaging that will help you to find the right tools to analyze that. And lastly, I want to talk about the tool, the pipeline XplorASL, that I helped to co-develop as an example of how we are trying to put all this together. So I'll start with the BIDS, the brain imaging data structure. So as I said previously, the issue is that with the neuroimaging data that very often each researcher stores, describes, and organizes the data in its own way. So he has his own system, how to organize the file, how to describe the metadata, and so on, which is perfectly fine if you're the only one who wants to analyze the data. But once you want to share the data with somebody else, this might become quite tricky for him to just be able to work with the data. And it becomes even more tricky when you want to use the data from several labs, and each of the data set is stored in a different format. And of course, you're not going to face issues how to sort all these data, but very often they'll also be missing metadata because somebody forgot to save it, or there'll be some metadata that it's really unclear what exactly it is as a parameter and what meaning it has. And so essentially what you really want to do is you want to take the heap of DICOMs from the scanners and organize them in a nice way where everything is perfectly described according to some standard. So the subjects, sequences, sessions, and all their metadata are organized in a nice way that you could just find your way in that easily. And this is what BIDS is trying to offer to the users. So BIDS is basically proposing a specification of how to work with all this, how to organize your data, how to save them in folders, how to name the files, and how to provide the metadata, and how should each of the parameters you need to know how it should be called, in what fashion it should be stored, and so on. At the end, it's pretty straightforward. The data are just organized in a hierarchical structures in subject directories. Then all the different sequences are organized into different folders, and for each sequence then you put all the necessary files for different sessions and all the scans needed for that specific sequence. Like you see here for the ASL, you have the basic ASL sequence and the calibration scan. In BIDS, the format to use to save the imaging data is nifty, and the metadata is saved in the JSON sidecar, which offers a human readable format. And the first nice thing about BIDS is that there's a validator to validate your data set. So once you put your data in the BIDS format, you can validate if the data are stored correctly, and also if you've provided all the metadata and if all the required metadata are present, which helps you to check that you've provided all the parameters, and then later on, once you share the data with somebody, he won't be emailing you asking you what this and that parameter was that he needs for the quantification. And so once you have the BIDS, your data in the BIDS format, then what you can do with that is that, of course, you can immediately start to share the data, or you can use it to archive the data. But what is really nice about BIDS is that there's the whole community. So it's not just a standard with the definition of how it should look like, but there's much more resources available. So there are example data sets. There are manuals on how you should create your data, use the data, and described in the typical caveats people are encountering with this kind of data. And what is most important is that there are the BIDS applications. So the whole philosophy is that if you save your data in the BIDS format, then any application like a free server, SPM, and so on, if they are designed to work with that kind of data, you'll just make it very easy to execute it on that data, because you won't have to reformat the data, reorganize it, set up parameters so that it works with the specific program, because it will already be provided in a structure that is known for the specific software. So that way, once you start using the BIDS format, you put the data in the BIDS format, it will be very easy for you to process it with any given software that supports it, and also to share with other people that will be able to do the same. So once you have the data in a nice format, then of course comes the question of what app, what pipeline or software you should actually use to work with the data. And with ASL, there's plenty of pipelines, so it might be quite tricky to start testing a few of them before you find the right one for you. So this is a task we wanted to address in the OSIPI, the Open Science Initiative for Perfusion Imaging. So this is an initiative that wants to create open source resources that will aim to eliminate duplicate development of the software, and also improve the reproducibility of softwares and speed up translation of perfusion methods to clinics. So what we've done in so I want to talk about what we've done in one of the task forces of ASL. The first task force called ASL Software Inventory. So in that task force, we want to address the issue how to help the users find the right tools to process their ASL data. And so to do that, we aim to first create an inventory of ASL pipelines, where we will just list the main features of the pipeline. And then we want to also test how easy the pipelines are to use, so that the user will know what he's if he's going to be able to use a pipeline that he chooses himself. So we've already done most of the work. So we first constructed the pipeline inventory. So we've basically approached all the known ASL pipeline developers, and we've also broadcast it to the community. so that all people that developed a piece of a software for ASL processing can fill in an online questionnaire. And at the end, we were able to list 21 different ASL pipelines. And we now provide tables with the basic information of what is the pipeline, where you can find it, whom you can contact if you have some issues with that. But we also list basic information of what are the software requirements, hardware requirements, and what kind of data formats each pipeline can analyze. And finally, we also provide a list of the basic features, like what kind of ASL types it can process and what kinds of outputs and inputs it is able to handle. So with this list, the users, if they're searching for a software to analyze their ASL data, they'll have some basic understanding what pipeline is good for them and what pipeline is not a good choice, because either it cannot read the data or it cannot process the exact data type they have. But of course, this list doesn't yet answer the issue of will I be able to work with the pipeline? So it only answers the question of will the pipeline be able to process my data, but not if I will be comfortable to work with and able to use it. And so this is what we've done in the second step of the pipeline evaluation. So we just took out of the 21 pipelines, we've selected the ones that are publicly available and still in the process of active development. And we've evaluated the ease of use of the pipeline. So basically, if it has a manual or if it's well documented, if it has some tutorials and easy to set up and download. Then we've also evaluated what kind of skills you need to run the pipeline. If you need to have some special technical or programming skills, or if it's a very simple to use pipeline that has a nice graphical user interface and anybody can use it without any ASL experience or programming experience. And lastly, we've also tested the flexibility if a given pipeline is able to process different kind of data set, large data sets with different kind of sequences and so on. So basically we're trying to sort of evaluate if a given pipeline will only be able to process very simple data sets or complicated data sets composed of data from several centers, and if it's going to be able to process it nicely in a batch mode. And so all these OSIPI resources, the list of the pipelines and their evaluation are now going to be online, and we will soon submit a publication that provides all these lists, and this should answer the users the basic issue of how to find the proper pipeline for them, but it should also be as a motivation to the developers to improve the weak spots of their pipelines and to provide them feedback. And yeah, as a last thing I want to talk about our pipeline for ASL data processing called Explore ASL, where we've tried to create something that will be easy to use, flexible and open, and that will be also adapted to be able to process large data sets from several centers without giving too much hard time to the user. And our approach was essentially to create something that will be able to do all the necessary steps for the users, starting from the DICOM conversion, ending at generating tables and graphs at the end, so that even a user that wouldn't have too much experience with ASL would be able to run the data and get all the necessary outputs and be able to focus just on research and not on nitty-gritty details of ASL data sets and images. And so I want to mention just some basic interesting features. So we have a module that helps to convert DICOMs to the bit format, which is not so difficult for general MRI data, but is still in the development for ASL. So we have roughly 50 different kinds of ASL data sets that we are able to process, and there are quite some differences between them. So it has not been an easy process to make it all work for all different sequences. We are also providing some special tools for quality check, so that the user can very quickly go through his data set and check the data quality without having to open every image in a viewer. And we try to offer all the processing steps starting from DICOM and ending at analyzing perfusion at different anatomical rows, so that we can generate tables and graphs right at the end. And to keep the development open, we've based the development on MATLAB, and we support all the major operating systems. And for those that don't have MATLAB, we're also working. We also have a compiled version, and we work on a Docker, and we are now working on a cloud solution that will be available also for the hospitals. To keep the development open, we have everything on the GitHub, so that anybody can open new issues or contact us through GitHub. And we also provide manuals and tutorials for the user. And as the last thing, we've recently developed a GUI that goes all the way from import to processing of everything, and it ends up creating graphs, tables, and it has also some nice features that you can create graphs, scatter plots, and at the same time you can click at each point of the generated results, and you're able to inspect the specific image data. Okay, so to conclude my talk, you should take 3 basic messages from my talk. So if you want to, if you have ASL data and you want to share it with somebody, then you should go for the ASL BIDS extension. If you're new to ASL and you're looking for new tools to analyze your data, then you should go to the OSIPI webpage and look at the ASL pipeline inventory. That will help you to find the proper tool for you. And if you haven't found a proper tool for you and you just want to, then you can try our own tool that should hopefully provide all the necessary steps. With that, I would like to thank all the people that were working on the initiatives in the OSIPI, in the ASL pipeline task force, but also all the other OSIPI members, the people that were preparing the ASL BIDS extension, and also the maintainers of the whole BIDS. And I would also like to thank the Explorational team. Thank you.
Thank you, Jan, for your talk. So I think we have time for questions. While we're waiting for questions, I can ask one. I've heard of the BIDS format a lot, but never use it myself. So is BIDS only a format, or does it provide software for the actual conversion from DICOM to BIDS? Because you mentioned there is ASL BIDS extension, right?
Yes.
That's a software extension.
Yes, very good question. So basically, BIDS is just a specification that specifies how to store the data and how to provide metadata. But there's a whole community around that is trying to develop tools that will do the conversion for you, and also all the existing tools for processing different kind of MRI data are being adapted so that they work with the BIDS standard. So, for example, the most well-known tool, DICOM to Nifty, is now able to provide not only the Nifty output, but also the chain-set output. It's not doing the perfect conversion to the bits and structure and folders, but there are some other tools that can help with that. So many of that is still in the development, but a lot of tools are already there, and a lot of tools are already supporting it. That being said, BIDS is not just MRI, it's also EEG. There are extensions for PET being developed, and all of these are in different state. So for example, ASL BIDS has been created and published about a year ago, but some other structural MRI data has been there for much longer time, and PET has been merged only recently. So yeah, it's still work in progress, but it's on a good way, and many tools already support it. So
yeah, so the conversion itself can be specific to the sequence itself because of the different sequence parameters. Is that correct?
Yeah, exactly. So it's mostly the sequence parameters. That's why it's very easy for structural MRI that has most parameters inside the DICOM, while for ASL, you not only have to go for the DICOM, but you have to find the data here and there in the PDFs, and that can make it more tricky. But the point is, once you do it, then you have the complete data set in a nice format, so you can start from there.
Yeah. So BIDS with the B stand for brain, I assume. Is that absolutely
That stands
correct?
for brain, yes.
Is it only for brain imaging? So for MRI data, for example, of body imaging, and then you cannot use BIDS.
Yeah, well, I'm not sure if I can really answer that question. So from what I know, it really started with the EEG, MEG, and fMRI. So people basically started to use it for the brain. But I mean, it can definitely be extended. So yeah, even body imaging can be saved in Nifty. And if you have all the proper parameters that you need, then in theory, there's no reason why it couldn't be used or extended for body imaging.
Yeah, that's great. So Eneko has a question. So how stable? So Eneko, do you want to ask a question yourself?
Sure.
Yeah. So for the yeah.
Go ahead.
Yeah, please. You want to? Yeah. So how stable are the recommendations for the ASL derivatives? Well, not. I would say not stable at all, because the ASL derivatives have not yet been defined, as far as I know. So, just to explain, there's the basic BIDS definition of how your data should look like, how your input data should look like. But then there are the derivatives, which are the files and data that are calculated based on your input data. So one thing is the raw data, the sequences as you acquire them, and the other are the derivatives, which would be the CBF maps or arterial transit time maps. And for those, there is no definition yet for ASL.
Thank you.
Great. So I have a last question. So you show this pipeline inventory and compare the user interface, easy to use. But I didn't see a criteria for accuracy. Isn't that an important evaluation or comparison of the methods as well?
Yeah. Very good point. So we specifically tried not to do that. So there's another task force in OSIPI that does challenges. So they've been trying to address the issue of the accuracy, and they've been organizing challenges to test the pipelines, but they decided that in the challenge, each team enters by itself and does the challenge by itself. While for the ASL inventory, we specifically wanted to test the pipelines ourselves by somebody that has no experience with the pipeline, so he can like provide a non-biased assessment of how easy it is to work with it for a new user. But at the same time, if you're a new user, then you probably will not configure everything correctly. So on purpose, we didn't want to evaluate accuracy so that nobody can accuse us of not using the pipeline properly.
Okay.
But yeah, other people
Yeah.
are working for that. So,
I see.
there'll be some MRI manuscripts soon.
Okay. Yeah. So accuracy is not in the scope of your inventory comparison.
Yeah,
It's for another
not in the
challenge
scope.
study.
But
Okay.
yeah, it's
Yeah.
within OSIPI, so there are much more things going on there.
Great. Awesome. So I think Marcel is getting ready. So we'll move on to our last speaker for this session. So Marcel will also talk about BIDS as well. So BIDSCoin, coin your imaging data to BIDS. Okay, I think you're muted, Marcel.
Hi, so can you hear me now?
Yes, we can hear you now.
Okay, I was just escaping my living room because there were some constructions going on. I hope it doesn't interfere with this session. Yes, let me share my screen. So I'm gonna do my entire screen. So I think you should be able to see my screen now. Is that correct?
Yes, we can see in full screen.
Okay, great. Well, thanks for the invite. Yeah, thanks. Also, the previous speaker, they already gave an excellent introduction to BIDS. I'm going to talk a bit more about it and do a very, very short, even a little bit of a demo. So I'm going to talk about how you get your data to the BIDS format. So, and with that, I think my screen is not moving. There. So with that, I like to go back a little bit and compare BIDS to DICOM and to see what DICOM has actually done for the clinic, and maybe compare it a little bit to what BIDS can do for scientific community. So typically, when a patient goes into a hospital, they can go into we call it a windmill of examinations. So you can have many kinds of vendors selling different machines that get data from you and which is evaluated by the clinicians. And before DICOM was invented, this was a big problem because the many vendors, they had their own formats and they wouldn't really, it was a big problem actually to get all this data integrated into a single data flow. And exchange data between the vendors was a big problem, and therefore DICOM was invented. And DICOM is a standard. You might all know it very well, but what I like to highlight, it's a patient-oriented standard to not just to describe the data, but a lot more. But there's a hierarchy which is centralized around the patient, and a patient can get different examinations called studies. And inside a study, many series can be taken, and which is kind of different kinds of scans, for instance. And in there you have multiple images. So there's a nice hierarchy in DICOM, which is solving a lot of problems that I was mentioning. So it makes that different vendors are using this format, and therefore they can go into the single archive system. They can be exchanged between workstations, many more things. Data can be sent from hospital to hospital or from department to department. The exchange of data is taken care of. But so importantly, it's patient-oriented, but it's not a file format. It's a standard to communicate data, to store it, and to even to print it or to display it. So it's a lot more. So this is great. That solves a lot of problems. So one can ask, why are we not adopting this standard for doing scientific research? For instance, I'm from the Donder Center in Nijmegen, and there we have a lot of large neuroimaging. We do a lot of large neuroimaging studies, and nobody is using this standard, whereas in principle it has a lot of nice features. So why is that? Well, the problem is, first of all, it's patient-oriented, and typically we don't do single subject investigations, but we have many subjects in our study. So, and it has a lot of features we don't care about, which are very important for the clinic, but not for science, neuroscience, for instance. And therefore, also a lot of neuroscientific packages that don't do DICOM. So you already heard in the previous talks, they work, a lot of them work, for instance, with NIFTY. And also, DICOM is the problem of keeping personal information separate from your scientific data is a lot larger in DICOM. And well, different vendors, DICOM is a standard, but it's also very complicated. So we want to get rid of all these nested structures, and also we don't want to read 4,000 pages to work with it. So the previous speakers have already mentioned the great advantages of BIDS, but I will go over it from this perspective a little bit more. So the BIDS standard was invented, and well, one of the big differences, for instance, with DICOM is that it's now study oriented. So instead of keeping the center of the root is a patient, now it's actually a study is the root, and then you have a lot of subjects in there, and each subject can have a session, for instance, which is in DICOM speak, you could call that a study, but that study would be on a single patient, but we have a study in a higher level. And then we have the BIDS data types. This is also mentioned. So this is not just about MRI, but we have MEG, PET. We have lots of, this can be extended, and it is actively developed also to be extended. So we have BIDS data types, and only in there, we have our data. So the BIDS standard is not, so this solves, again, a lot of the previous problems. So, and because now, this is extended beyond MRI also, but also beyond the private header. So this is all standardized a bit more so that the remaining vendor interoperability is reduced. And this is a description of the study. And therefore, it also aims to improve the repeatability and reproducibility of studies in the field by describing all the metadata, the way this was, the data was acquired, and which helps a lot to share the data. But I would also like to highlight, it's not, so the BIDS standard is very good for data sharing and for pooling data and so forth, and reproducing your data, but it's also very, very important for sharing software. And that's because if your software can work with this standard out of the box, that means that also other people develop software that works with your software. So it's not just about sharing of data, but BIDS is also making possible that makes it easier to share software between institutes, for instance, because that will work on their data as well. So it's definitely not a file format, but it's a study-oriented standard to store the brain data, brain imaging data, but not necessarily just brain. It started with brain, but it can be extended, as was just discussed. So this you're also seeing. So this is the goal. So we have, in this case, we have DICOM data, and that's well, this organized in a certain way, and it needs to be organized according to the BIDS standard if you want to take advantage of for scientific research. You want to make it more easy, we can organize it this way, and then we can apply all many software packages that understand the structure. Now, to go from, for instance, to DICOM to BIDS, or maybe many more file formats here, because this is not just about DICOM. There can also be presentation log files. There could be EEG data, MEG data, and so forth. And to get everything into bits, that shouldn't really be a hard problem. Actually, it's not. I work in an imaging center where there are a lot of medical students, psychology students who are not really interested in converting the data into bits. They want to address their scientific questions. So they need to get into all the details of these file formats and also of the bit standard before they can actually start analyzing the data. And that part to get that data into the bits format, that shouldn't really be a hard problem. I think we should make an effort to take that away from them a little bit, from the PhD students who already have a lot of on their plate, and the supervisors, they usually don't care too much with that, so they just make it a problem of the PhD students. So my goal is to make that problem a little bit smaller. So, for instance, what I don't want is PhD students to start programming, to writing code, and to study the bit standard in detail, to follow many steps to get their data into that format. And for every study to do it again, and they get a new imaging modality, they have to do it one over, and they have to learn about physics and about all sorts of transformations that we don't want. So I see this problem to getting your data into bits as not as a rule-based problem, as you can see here. Here you see a couple of rules. If this, then that. So if there's certain properties of the scan, if there's certain, things like echo times, repetition times, all the MR physics is in there. You need to have that knowledge in order to get it into the right bits data types. But this is not what the user typically knows, at least in our center, or that they want to know about. But they definitely know about their own experiment. So in their head, they certainly know that I made a scan, which is an anatomical scan. And then I made a functional scan with a certain task, and they certainly know how the task was called and what the purpose was. So they have a lot of knowledge about their experiment, but it's not on the level of the MR physics. So it's more at the level where they work on the console. So they have a knowledge about how the data should be mapped from raw data into that bits format. The only thing is that they don't want to do, or they don't know how to do, is to make it into programmatic code. So, but they have this mapping knowledge. So this is what I aim to exploit. So I want to have that, to tap onto that user knowledge on how to convert that data, so in a simple way. So this is how I came up to develop a package called BIDSCoin. So here you see a schematic overview of its working. So here in orange, you see a layer which I call the BIDSCoin layer. This is actually what the user is seeing. So the user has, there are basically 3 steps. I will go over them a little bit. And that 3 steps that they make a map of your data onto bits and then do actual conversion. So how does it work? Well, first, there's something called a template bits map, which is containing prior knowledge on certain data types, on how they are generally converted into bits. And that there are then mappings. For instance, if you do MRI, and you have a protocol that contains a substring called T1, that's typically mapped onto a anatomical T1 data type in bits. So you can put it there, and then you can run the bits mapper that uses this knowledge and does some data discovery. So what it will do, it will scan your entire data set, and it will use everything which is on disk. So it will try to use all the information there. So it will read file properties, like how many files are there, or what's their size. It will read the DICOM headers, for instance, or if it's not DICOM data, it can also read any kind of header as long which is provided by the plugins. I will come back to that a little bit later. So basically, it will do a data discovery for you automatically. So it will like make a fingerprint of every time a new data type is encountered. It will make a fingerprint, put it in the study bits map, and then it will go on until it finds a new fingerprint, and then it collects a list of data types. and that data types are then automatically sort of, that comes off from the template. So they're like automatically mapped onto bits. But not everything is stored digitally on disk. So a lot of users, they have knowledge about their experiment, and which is not in the data. This metadata, which is not in the data on disk. So they know it. And that's why I made a GUI so that this mapping can be adjusted, can be extended with that knowledge. So you tap onto the user knowledge in that second stage with the GUI. So you try to, so they can optimize the mapping. And then in the final stage, all the information is collected. They can just do simply an automatic conversion of all the data in the repository onto bits. And I'd like to also point out a little bit this plugin architecture that you see here in green. So below that, so because this is a kind of an abstract layer, and all the interactions with the data is done through plugins. That means that what I just explained to you about this data discovery uses just file properties and header attributes, but this is done through plugins, so it doesn't know about the data format. So, for instance, BIDSCoin, I wrote a plugin for the DCM to NIIX, but also as William Clarke just showed you, he wrote a converter for spectroscopy, spec to NII. I also wrote a plugin around that converter. So for BIDSCoin, it doesn't really matter which converter is used. It just takes, as long as the converter, as the converter can provide metadata, it can be used by, and it can convert data, obviously, can be used by this framework. So it's very flexible because of this. It can be extended to multiple data types, and yeah, for the user also, it doesn't really matter so much which kind of data you have, because the user will get a unified interface to edit the mapping onto bits. So it will see the file properties and it will see the header fields. I will show you in a while. Yeah, actually, I'm going to show you a little bit now. So there's only two commands that on the command line that the user needs to know. So the first one is called bits mapper. Just give the location of the data and the input data, let's say, and the output data, the bits folder. That will do scan your data. It will also launch a GUI to modify the mapping. And then if that's all fine, the user can run the second command, which is called the BIDSCoiner, which actually does the conversion. But that's what you see here. So that template bits map is then used to scan the data. It goes into the study bits map, which is edited by the user, and then the BIDSCoiner just takes that information to do its job. So only here data is converted. So now I'm going to do a little bit of a demo to see how to show you how easy it can be, and I think also how easy it should be for the average user to convert that data into bits. So I'm going to open up a little terminal here. I think I need to get screen. Yeah. So I have a little terminal, and as you can see, I have some raw data here, which is DICOM data in this case. It's a subject where we scan some data. Well, here there's a lot of data, and there's anatomical data. There's some functional data. There's different data sets. So I'm going to run the bits mapper just like this. So I'm going to say, okay, I have a raw folder, and I want to have some output in the bits folder, and then go over the data and see what we have. So that's all you need to do. So it starts to find new samples in the data. It goes over it, and it comes up with a graphical interface where you can see a short list of all the different input data and how that goes onto, so the input data on the left and how that goes onto bits output data. Now, as an example, I'm going to open up one of the mappings, suggested mappings because maybe you want to modify it because you know that the task was not CMRR 2.4, but it was just a Stroop task. You just can change that, and you can see the output changing immediately. And you can also say the task was Stroop with, I don't know, condition 1, something. So you can put some metadata which will be in your BIDS structure. Now, to make life easy for users, so they don't need to study the BIDS format in detail, I put a lot of effort in providing help about all the BIDS entities. So with descriptions, you can go to help pages. You can also have a look at, for instance, at the DICOM header to see which attributes there were there. As you can see on the left here, these are the properties that were used to identify this data type. These are the file properties here. There was a selection of DICOM attributes that was used to identify this data type. You can change. You can say, okay, this was wrong. This is not the functional scan, but it was anatomical scan. And this is all dynamically adjusted, and also it limits the choices that the user can make. So it doesn't give all the options that are possible. Only for this data type, only the right BIDS entities are presented to the user. So you can do something that that's valid according to the BIDS standard. If you do this and you can save the BIDS map, all you need to do is run the BIDSCoiner like this, same command, and it will go into do the conversion. This will only take a few minutes. In this case, it's calling the plugin. So this is DCM2NI, but there's also running spec2NI, for instance. And this will go on for a few minutes. It's all logged. Let me go back to my presentation. Yeah. So, well, given the interest of time, I would like also to conclude to have shown you, hopefully have shown you that the BIDS standard is a great promise for doing neuroscience on a large scale in an integrated way, similar to what DICOM has been doing for the hospital. But BIDS can also do similar things for the neuroscientific community, for storing and sharing data. And yeah, but the mapping strategy can be very effectively used to convert your data. And BIDSCoin is one of the tools out there, but I think it's set up to be very flexible and user-friendly. So if you don't know how to program yourself, this could be a very good way, yeah, to get your data into BIDS and to start using these BIDS apps to process your data, and then you can focus on science, addressing scientific questions that you're really interested in. We also wrote a paper about this, so if you want to know more about it, you can go to this Frontiers in Neuroinformatics paper to see a bit more about the possibilities and about the powerful features that I didn't mention that are in there. And also, of course, I try to make this as open as possible. So it's all on GitHub, and also there's documentation on the Read the Docs page. And if you have any questions about it, you can, on the GitHub page, for instance, you can open up issues. I will happily yeah, help you out there. And yeah, that's, I think, I'd like to conclude.
That's great. Thanks, Marcel, for the talk. So you're now going to show us the sorting result after.
Oh, you want to have that? Yes, I can.
BIDSCoin.
Yeah, I can do it. It has finished. No,
Okay.
I can do that.
Yeah, just curious.
So
what it
go
looks
back
like.
to share my screen then.
Mm-hmm.
So indeed, in the meantime, it has finished. So I can, I think you can probably, let's see my screen now. Yeah. So it has finished. So it also does.
Yes. We can see now.
So, I spend a lot of time in logging. Also, all the errors and warnings and all the conversions out there. So you can see here a summary of the processing, and there were some warnings. So I also do a lot of bits validation. So, for instance, it warns here because I also edit it freely without taking too much care. So it warns me that not everything was bits valid. And for instance, here there were field maps that were not that didn't contain intended for values, for instance. So that in the bit standard you need to specify what the field maps should be used for, so that packages can run out of the box. I didn't do that, so it warns me that it's not wise to do that. In this case, this was all the warnings. And you can also see what I have now. So I wrote out in the bits directory. So you can see this is now the newly generated data. So there is a bit structure. There's a stop README file that you can modify yourself to write more about your study. There's also here a BIDSCoin folder with all the logs in there. So all the transformations, how they were done, they were all there. This is where all the mappings are stored. There's also a dataset description where you can put more metadata about your study, which participants were in your study, what age they had, what weight they had, and that you have, for instance, for this subject, you had an anatomical scan. This was all automatically done out of the box from the DICOMs. And here I don't know if you remember, here I typed in something random. You can see it's over here. I also made a lot of effort to this toolbox was tested with many data sets. So for instance, in the past I tested it with complex data that had magnitude, phase, multi-echo field maps. So multi-coil, it was multi-coil, multi-echo, and it had magnitude and it had phase, and it was a field map. So that these things, they produce a lot of it's quite complicated to deal with that automatically and to put it into bits, but I made a lot of effort to make these this very robust and work in many scenarios. So as you can see here, this is it all generated this result. It was just a small data set for demo.
Yeah, I'm pretty sure this is a lot of effort that you've made.
Yes, it's a lot of effort, and I do this indeed. Also, I put a lot of effort in the documentation. So I have an extensive read the docs page, and but I think also, for instance, this read the docs page, it's a lot of effort to make it, but also saves me effort because I get less questions from users because I can point to the documentation. So it's worth developing a good documentation. And not just to put more and more information on it, because then users will stop reading it. So one of the design things I also put in my code is, for instance, in the editor, I put help where it's needed. So where you are working at this point, you want to help, targeted help, and you don't want to have like many pages of help that you have to go through to find your question. So that's indeed a lot of work, but I think it's pays off.
Yeah. So is it possible for others to contribute to your program?
Yes, I have several contributions, but I'm the main author of the package. Mm-hmm. But I would love to have more contributors because I'm not sure if it's very well known, BIDSCoin, but I think because of it's a Python package, so it should be it's multi-platform. It's many people can I think install. It's on pip, so you can do pip install. Many people can install it, and to contribute, you need to have Python knowledge. But I'm very happy to have more people on board to develop this further, and especially because it has this plugin structure, so you can start writing your own plugin if you have a converter and you don't have a good interface for people to convert their data to bits. You can use the bits framework. You write a plugin, and you benefit from the GUI that I wrote and from the other plugins.
Yeah.
So
yeah,
also,
there's
for instance, I also had people in the center that wanted to convert existing Nifty data sets into bits, and I thought, okay, NIBabel can do that. So I wrote a NIBabel plugin. So yeah, that took me a couple of maybe 2 days. I had a NIBabel plugin. So everything that NIBabel can convert, you can run it in BIDSCoin.
Sounds good. So yeah, has a comment. Do you want to do that yourself? Yeah.
Let me see.
Yeah, very nice work. So I was just wondering about these extensions, but you probably answered that already. If you want to add a new extension, then you have to write a new plugin that is able to handle it, right? You cannot just put some sort of mapping between DICOM and BitStacks. You have to put in a whole plugin.
No, so there's 2 things you can do. You can write your own template. So in the template, there is prior knowledge about how data types should be converted into bits. So that's basically, it lists things from the header, like it lists file properties. If you want to use that, like a file name, or if you want to use something in the header, you just put it in the template and you tell it which bits entities should be used according to the standard, right? But that's in the template. But to do the actual conversion, to interact with the data, you need something like spec to NI or DICOM to NI to read attributes from the header and to do the actual conversion. So that's why you need a plugin to do that. So I think typically most users, if they want to have.
Yeah, sure. No, I think I understand. So you can use DICOM to NI, and then you can tweak it using the templates, for example.
Yes, and that's a lot easier. You don't need to code. You can put regular expressions in there to put some power, but yeah, it's a bit too far. I think it's
useful and easy.
I don't want to go in too much detail to show you the templates, but yeah.
Great.
Yeah, I can imagine how it could look like. Thank you.
Yeah, I mean, Bitcoin is definitely popular, so I hope your BIDSCoin will getting popular too and will be a success in the future. That's a nice name, BIDSCoin.
Okay, thank you.
Love the name.
Yeah.
Yeah. All right. If we have no further questions, I want to thank the speakers again, and then we will conclude this session, and then we can continue our virtual social events on Gather Town. All right.